Okay, this is going to be EE3113 that. Okay, and show me the. Okay, so you're going to have, you're going to have your signal source, and then you have what is called a coupled capacitor. So this thing, and then you're going to have that resistor, that resistor. These are your biasing resistors, and these 15 volts. Okay, and then you have, that's your base. I like to call this RC for arc collector. I like to call this RE, and then either R1 or R2. And this little arrow goes like that. Okay. And then the design says, and usually when you say gain, it's A sub V. That means it's going to have voltage gain. And he's got a negative 3.3. Okay. And then he's got a I collector, and then Q. Q means quiescent current, meaning that if you don't put any signal, that it's the steady state. In other words, remember when you do the spice simulation, we do an OP, and it gives you the voltages on the spice. Okay, that's quiescent. In other words, you don't have any voltages, so that's OP, operating point. It's quiescent. In other words, that's the current that the transistor's called driving. Oh, I'm still sick. Okay. So then, let me see. Okay, and what's the quiescent current that they want? Okay, 2 milliamps. Yeah, I got that. I got that. Okay, and RC, what they set it to? 3 point what? Okay, ohms. Okay. Yeah, this one. Okay, you gotta remember this. Since the signal is coming in here, and when I say a signal, you're gonna put a sinusoidal wave. Right. But see, this is base, collector, emitter. Okay. So the signal is going to come out here, but the signal is going to come out here. This is going to be V out. This is going to be V in. Well, no, it's think of it this way. It's going to be, you can think of it as a box. It's an amp, an amplifier, like a stereo. Okay, and you have a load. This is V out. This would be your speaker. You can have an 8 ohm speaker. So this, and this could be your microphone mic. So you feed in, and it comes out. So it goes in as a weak, and it comes out as a strong. Okay. Well, that's what this is. This is an amplifier. Okay. But okay. Well, you have to remember the name. There's 3 topologies. Okay. There's going to be 3 types. 3 types. There's the common. You're going to have to learn this by heart. Common base, common emitter, common collector. Okay, so the way you can tell what this is, okay, it's coming in through the base, okay, or at least some of the signal comes through the base, and then some of it goes through the emitter, and then the output comes from the collector. Oh, and usually you have a load here, fictitious load. We can call it RL. Okay, current gonna come here, but it returns through the base. So this leg is common to the base and to the collector, so they call this the common emitter. So you can think of it this way. Okay, signal is coming into the base and it's coming out of the collector. Which is the terminal not used? Yeah, the terminal. Which of the okay, signal comes in the base and it comes out of the collector. Which is not being used? So the emitter is common to both base and collector, so it's common emitter. Okay, so you can have the same thing. Let's say you have this. EDD, and then you have let's say capacitor, a signal source, and let's say EN. Here's the base, here's the collector, here's the emitter, and then right here that's V out. So the signal's coming into the base, but this time it's coming through the emitter. So which is not being used? The collector. So that would be a common collector. So it's basically the circuit is basically used to where current is not actually flowing. Yeah, the one that's common, the one that's not being used, that's the node that is common to both the input and the output. Okay, so that's what those are. And the same thing, like for example, let's say right here. Hang on. Okay, so we got that far. So let me do this. Let's erase this. Okay. Yeah. So you said right here that at times, if current's flowing, well, obvious reasons, the current flows out from the base. You told me yourself that if it flows out of the emitter, then it's a common collector. If it flows to the collector, then it's a common emitter, right? Yeah, the one that's not being used. Yeah, the one that's not being used. In other words, think of it as wherever the signal path, if it comes through the base and it comes out through the collector, then the one not being used, that's the common emitter. Let's see, here's the thing. Here's the question. If you, knowing that though right here, like in general, if you were to do transistors wise though here, how do you know what current is flowing? How can you tell whether it may be flowing out from the current or whether it will flow out from the emitter? Well, it's wherever this thing goes, wherever your signal path, VS. Here you can have two outputs. You can have an output here or here. Wherever you take the signal, the signal comes out here, come emitter. If it comes out here, come collector. It'll make more sense in a little bit. Okay. Now, but you didn't know what I mean. Yeah, but there's no simple. Okay, the rule of thumb, when you have a circuit like this is AV, and I'm gonna say that it's an estimate. Okay, the gain of this is typically RC divided by RE. That's it. So it's the ratio of that. So this one is supposed to be 3.3. And if he wants, okay, so he wants 3.3 as a gain. is equal to 3.3K divided by RE. Okay, so that means that RE has to be 3.3K divided by 3.3. Not forget about that. So basically, what's that? It comes to 1. So you got 1K. So that means this is going to be 1K. That's 1K. No, no. The gain, this little negative, means that it's out of phase.
Oh, out of phase.
Yeah. So in other words, if you put a sine, you'll get a cosine.
Oh, so in other words,
it'd be like this. It's going to be the opposite. They're going to be the inverse. It's going to be the inverse. Oh, didn't do the inverse. Okay, it's going to be the inverse. It's going to look like that. So this would be Vn. This would be V out. And the negative, see this negative where he says this? That means inversion. Inversion. Invert.
oh,
Out of phase. Okay. Now, so when they say IQ, this current, remember this is positive? The current is going to go in this direction. And that is going to go, so that means this is positive, negative. So you can always say this is another rule. That the current is almost equal to IE. So this is IE. This is IC. So whatever current this flows, that's got to be the same or close to it. Okay. So when he says ICQ is equal to 2 milliamps, okay. Well, if IC is equal to IE, and he gives you the IC, which is collector current quiescent, is 2 milliamps, what does that say about IEQ?
That means IEQ has to be the same.
It's going to be 2 milliamps. Okay, so now you have Ohm's law, right? Voltage, and you say VE is equal to IEQ times 1K, right? Okay, so what is IQ?
Oh, 1K meaning the resistor.
Ohm. Yeah.
The resistance of the
Right. So now IE, and we can call it IEQ. Okay. What's IEQ?
IEQ is 2 milliamps.
Okay, so we're gonna put 2 milliamps here times 1K. So the K and the milli cancel, so you have 2 volts. Coming with fever. Okay, so that means for 2 milliamps to flow, you need right there 2 volts. And if you have 2 milliamps flowing here, that means you're going to have 2 milliamps flowing there. Okay. Now, Have you covered diodes?
Yes.
Okay. So you have, what is this called? What's that part? That this is a P and that's the N. So what's this symbol called? Or this side?
Oh, I'm sorry. That's the anode.
The anode? Very good. Anode. And
That's the cathode.
cathode. Cathode.
CA.
I like to do it this way. So is it positive here or or positive over here?
Positive goes on the left side.
So there's a positive and negative. So how much volts takes it for it to turn on? To turn on diode on.
We have about 2 volts.
No. It's a diode drop. What's a diode drop? To turn on a diode, there's VD. VD diode, that's the drop across the diode, is approximately 0.7 volts. Okay? So there's a diode right here. See right here? So if this is, so this is negative, this is positive, and it's a diode. And if you have, think of it this way, you got 2 volts here, and for this to turn on, what voltage would that have to be for it to be on?
So I have 2 volts over there.
And you need a diode drop, so that means you need from there to there. So you got 2 volts here, so that means this has to be what?
Has to be,
Right, the base.
the base has to be VN.
No. What the voltage? You gotta sum up the voltage. VE is 2 volts right here. But then you have a diode drop. In other words, this is what I'm asking. Basically, it looks like this. You gotta learn this. Otherwise, you're gonna be in trouble. Okay.
Otherwise, why do you think I work hard?
Two. Well, yeah, but you should know this already. Anyway, so you got current going like this. Right here, that means there's 2 volts right there. And just think of this as a battery. Look, when the diode is, then it looks just like a little battery. That's a positive and negative, and it's 7/10 of a volt. So what voltage? If I got 2 volts here, and this is 0.7, what am I gonna have here?
Okay. So you're going to have over there
I got 2 volts here,
1.3.
and then
1.3.
no, but this is, look, positive, negative, positive, negative. They add up. They don't subtract. So what are you gonna get here?
So they add up all the way to make it 2.
Well, you got 2 here,
Mm-hmm.
and then you add what?
0.7.
So what are you gonna have here?
2.7.
Okay. Well, this is the same thing. You got 2 volts here. You have a battery here, basically, of 0.7. So that means this is going to be 2.7. Okay.
In volts.
Hmm?
In volts.
Yeah. 2.7 volts. Okay. Oh, and then there's another. Has he talked anything about beta?
He's mentioned beta a couple of times, though he hasn't really used it as much. What I've done here throughout my homework is that beta is mostly 100.
Okay. That's a good approximation. Okay. So let's go ahead and go to the next one. What the heck? Erase all this. I'm definitely taking a day off tomorrow. Okay. I'm gonna post this in the internet. That way you can see it. Okay. This is a little bit too much, too fast, but I'm giving it to you right now. Okay, I'm gonna do it again. This actually takes should take you the whole semester. Okay, so you have this. Hey, turn the fan on, please. It's burning. No, that fan that's down there. Yeah. Yeah, point it this way. Thank you. No, gotta connect it up there. Thank you, Güero. Morenito. Okay. Mira. So now we know we're establishing the current. We know that this is going to be 2 volts, and there's 0.7. So anytime you this has to be, you know how you know Ohm's law, left and right. Well, you gotta know diode.
So with the
You always, when anybody tells you how many volts does it take to turn on diode, the first thing you should say is 0.7.
so without a doubt, so even with no change, so even if this is different though, or even if it's not within a transistor, you're just saying in general with all diodes, in order for it to turn on, it has to be 0.7.
0.7.
So no matter
So
what,
there's a
that's
junction.
general term, right?
Yeah, a diode is going to be. So that means this is going to be 2.7. Okay. We said this is R2, R1. Okay. Now the thing is, beta means that this current, that's called base current. Okay. And this IC. Okay. Beta is actually a ratio of the collector current divided by the base current. So that means, let's say the beta, let's say IC equals beta times IB. Okay. So let's say beta is 100. So let's say if you have 1 microamp or 1 microamp, that means that IC is going to be 100 microamps. That's the current is going to go through there. So basically that's beta. Okay, but beta, we also, you're going to be using what is called small signal analysis. Okay, what's the resistance? The base. The reason is, okay, you want this. I hope I'm explaining it correct. Okay. So we want 2.7 volts. That means, see this voltage divider? You want to set the voltage divider accordingly.
Yes.
You want it where you get 2.7 volts. But
You don't know R2, you don't know R1.
but let's say let's make this 10K. Okay, so the current, I think it's what, 250 milliamps? Alright. 2.7 divided by 10K is 270. So that means you're going to have 270 microamp. That same current goes through here. So this is what I want to, hopefully you can see this. So 15 minus 2.7 equals divided by 0.00027. So that means to do a divider network, this would be 45.55K. Let's see if I got this right. Yeah. Okay, let's see if it makes sense. So 15 volts times 10K divided by 55.55K, it should equal 2.7. So let's see if we got that right.
55.55 because you did
Yeah. Okay. 15 times 10 divided by 555. 2.7. Yeah. Okay. Now, okay. You can do this, and this would probably work. But remember, this thing goes connected right there. And this, looking this way into the base, that looks like a resistor. What would this be 2.7 if this is also 10K?
Would that be 2.7 if that was 10K?
If you put another 10K in there? No. Because now this would be 5K. Two of these are in parallel, right?
However, if you
and then there would
5K
be 50,
right,
and that would be 50. So let's see.
However, if you did combine the 10, if you did combine the two 10Ks and add them with parallel with the 45.55, once you get the voltage of basically the 5K, you go back and say,
okay,
in parallel.
Well, hang on. Okay, well, if you put, this is the base. This is what the base looks like. It looks like a 10K. But if you put 10K here, then that becomes 5K because two in parallel, and then you add it to the 45. So that's the equation. Okay, so now let's see what we get. 15 times 5,000 divided by 50K. You would have 1.48. But we don't want one. We want 2.7.
Yes.
Okay. So that would not work if the resistance, if it was 10K. But what's nice about beta, the next formula that you have to remember, R base is about beta times RE.
So it's 100 times the emitter resistance.
Yeah. So what would it be?
Well, if you go back here, beta's 100,
Mm-hmm.
of course, and then according to our circuit, the emitter resistance is 1K.
Mm-hmm. So what would be the base?
So 100 times 100. Yeah.
It's 1K times 100.
Yeah, 1K times 100. Oh, 100 times 1,000. Sorry.
Well, just multiply 1 times 100. That's 100. Okay. So now, instead of, now we have this. It looks like 100K. So this thing is 10 times bigger than that. So it doesn't affect it. So now let's see if it, okay, let's see what the reciprocal are. These two in parallel, right? Okay, let's see what the voltage is. So times, did I get that right?
I think you only did that for.
Didn't do it right. Yeah, get your calculator. 10K times 10. I think it's like 9K.
Okay, so just say this.
10K and 100K in parallel.
Here it is.
What is it?
9,090.90.
Okay. Before it was 5K. So this doesn't, it doesn't affect it. It does affect it a little bit, but not as much. Okay. So in this case, we can do that. Or we can lower this. Okay. Now let's go ahead and do this. You said it was 915K times, what was it? 9 what?
It was
90 what?
sorry. It was 9,090. Or in this
Okay.
case, we can say 9.10 kilo.
Okay. And the summation. So add the,
4.55.
yeah,
5K.
plus this. 54.
Oh, I'm sorry, I'm adding it. Sorry.
54, 5,
That
6.
would be 2,495.
No, you add them. The 45, 45.5K plus.
I did. What I did is I multiplied the top one and then divided by multiplying by the 45.55.
No, hang on. I want the bottom. 45, 5, 5, 5 plus 90, 90. That's what I wanted to get here. So this is volts. So you got 15 times 9 that divided by 54645. So remember we wanted 2.7. Now it's 2.49 volts. Okay? So that's, I mean, it still affected it. We wanted 2.7. Okay, then we can do this. Let's divide this by 10. So in other words, 4.55K make this 1K. Okay. So now let's see how it looks like. So now we're making this resistance much lower than this. Okay. So now we're going to do the impedance of the 1K and the 100K. Okay, so it's 990. 990. Okay, so 990 plus 4.55K. And let's see if we get closer to the 2.7. 15 times 990 divided by 990 plus 4550. 2.68. So that's almost 2.7. Say,
If you round it out to the nearest tenth.
so what I'm doing is I'm making these much smaller. That way this impedance doesn't affect it. Okay. So now we know we can try both. We'll try the 4.55 and then we'll try a 1K. Okay. So now we do simulation. Hey, tell Vanessa if she can find the thermometer. I think I got a little bit of fever. Yeah, ask her if she can find. If she knows where the thermometer is. Okay. So right now we're not going to put, this is 3.3K. So to find out the QS, and you do OP, operating point.
That's what you were telling me about her in terms of history.
Okay, then we go here, view. Okay, there it is. See? 2.69. See that? Okay. And then the QS current. Look. See? No.
About the same.
Huh?
Almost about the same.
Almost the same. Okay. Now remember, we first we said this could be like this, but we said that then we're not gonna have 2.6.
Yeah.
We're gonna have, because of the impedance. Okay, where was it? 2.49.
Yes, that's correct.
Okay, so now we do it. Okay, this is 2.65. Actually, this has base probably a 200. Yeah. Actually, it's got a beta of 400. Copy that. And put it in the miscellaneous file. And we'll put this 100. VF means forward beta.
Forward beta?
Yeah. So now, when I run it, this should be more what it should be close to what we calculated before. See? 2.54. And I calculated 2.5 basically. It's just 2.54. So I'm off by what? 4 millivolts. That's not bad. Okay. So now he says put a resistor cap. He says make it 15 micro. Put a signal source. Okay, he said put a sinusoidal wave or what?
Said use the 500 millivolt.
0.5. At what frequency?
1 kilohertz.
And that's it.
And then a V sine part as input.
Hmm?
V sine part as input.
Oh, that means that's a sine wave. So it's a sine wave. Okay, so this is going to be, and we'll put a label, VN, and put V out. The capital. And then we'll put calc, no, pound. Auto, very good. Auto plot. And then it's a transient, plot 1. And we're going to V.
It's supposed to be trans and not trans.
Yeah, no, it's trans.
Oh, I thought it was trans.
No.
And that means when we go to simulation, we have to check the transient analysis.
It might work.
Oh, without it?
Let's see. So there's the statement. Okay, and he gave you the time step. I see. Oh, maximum 10 microseconds.
No more than 10 microseconds.
Time step.
Yeah.
10 microseconds. 10 microseconds. And this is milli. It's kilohertz. That's a milli. So you want 10 cycles. So you want 10 milliseconds. Okay. So now we should run it. And there you go. Okay. So let's do this. See, this is writing DC.
Yes, that's correct.
We can do it this way. Let's do the peak to peak. Well, we know that this is 500 millivolts right there, 500 millivolts down there. So the difference is 1 volt. See right there, 996 millivolts. So peak to peak is 1 volt. So this should be one. This is 1 volt, and you want a gain of 3. So this has to be 3.3 peak to peak. So we'll put that there. Put that there. Bring it over here. 3.2. Very close. Okay. So there's your data. Print it out. And this one doesn't label, so you have to put the stuff. So 3.2 peak to peak. I hope I don't get you sick. This is 1 volt. Peak to peak. Okay, so here's your data. Okay, so now he wants to do an AC analysis. So you go enable. You do that. Then you do AC. And what's the frequency that he wants to start?
The amplitude, set its amplitude to 500.
No, this is transient. It's the next one. Number 3. Oh, let me see. No, this one.
Oh, it says set up an AC sweep from 10 hertz to 10 kilohertz.
Okay, so 10 hertz.
And then 10 kilohertz.
10 kilohertz? Okay.
With 100 points per decade.
So here, 100 points per decade. Okay, so now you copy this, but now you rename this as AC. AC. And you want dB, decibels. And we'll do it both ways. We'll do it that way. This will be in dBs, and then this will give you absolute. You just put that. Okay, you go there. There it is. See? So here in dBs, a gain of 3 is actually, it's called 10 dB, 10.1. So you can label this. .13 dB. But then right here, this is volts. See? That's volts. And the gain is, basically you put 1 volt in, and you're going to have 3.21. See? 3.21. That's the gain. So you check the gain both ways. 3.21 volts per volts. That's the gain. And that's it. Yeah. That's how I work for you guys.